So this is a PowerPoint on aqueous ionic equilibrium, which is a kind of a different way of saying buffers. This is going to deal with buffers and titrations with acids and bases, and this is chapter 16. So the first application section that is in the beginning of your textbook has to do with antifreeze. An antifreeze contains the compound ethylene glycol, and what happens is if it is drank either by humans or a lot of times wildlife and pets, it'll give the initial effect of drunkenness, and then once it hits the liver and it becomes a high enough concentration, the buffering capacity of blood is overcome, which causes the pH of the blood to drop. You can no longer carry oxygen. You go through something called acidosis, and the person or animal will die very quickly. So what they talk about at the beginning of the chapter is how if you're changing the antifreeze or adding antifreeze to your car, which is kind of the number one place where you're going to use antifreeze, that you shouldn't just wash it, with the hose down your driveway into the sewer, because then it can get into the water supply. It can affect wildlife, and then you have to be careful of your pets, dogs and cats. If you have antifreeze, a puddle in the driveway, if they drink it, it can cause them serious harm. So first we're going to talk about what a buffer is. A buffer is a solution that resists changes in pH when you add an acid or base, and therefore keeps the pH of a solution relatively the same. Now, the term is relative. It doesn't keep it constant. It's not forever at the same pH, but it keeps it within a few tenths of a pH. It acts by neutralizing the added acid or base, kind of like it absorbs it like a sponge in a way. But it helps to keep the pH relatively stable. The number one place you're going to see buffers, you're going to talk about buffers, is in the human bloodstream. Your blood has a very finite range of pH through which it acts, so you have lots of buffer compounds in your blood that help keep the pH of your blood the same. There is a limit to how much resistance the buffers can provide. If you keep adding acid and acid and acid, there will be a time where the buffer is saturated, kind of like a sponge becomes saturated and it can no longer absorb any more of the acid, and the pH will actually jump quite drastically at that point. Many buffers are made by mixing a weak acid with a soluble salt that contains the conjugate anion that's also in the acid. So the number one acidic buffer you see normally is made with acetic acid. So you see here on the left you have the weak acid acetic, and on the right you have sodium acetate, which notice it has that acetate ion in it. The same in the acetic acid. You mix them together and you get, this would be an acidic type buffer. So how a buffer works is by neutralizing any added acid or base. It's essentially a very quick neutralization reaction. So remember this general equation at the top I told you is important. It's the acid, Ha, added to water is going to dissociate into the anion and the H3O plus hydronium ion, or you could put the H plus here. So a buffer works by applying Le Chatelier's principle. So when you add an acid, it kind of increases the concentration of the acid, and it causes the whole substance, the equation, to shift. You can also think of it as the H3O plus combines with the OH negative to make more water. Remember, water is neutral. But buffer solutions also contain a lot of the conjugate anion, and when these combine with the added acid, they make more HA and keep the H plus concentration the same. So the key when we talk about the way buffers work is this right here. The H3O plus is what's affecting the acidic concentration. Gets a little confusing because you would think, okay, if I'm going to add acid, it's automatically going to lower the pH, but not necessarily if that acid doesn't break up. So if the acid doesn't break up and cause or release H3O plus ions or H plus ions, whichever one you want to think of it, it's actually not going to change the pH. So what happens is if you add H3O plus, if you're adding an acid that's dissolved in water, what happens is that H3O plus actually combines with the anion, making new acid, which with the Chatelier, it's going to shift it to the left. So if we just kind of go on Le Chatelier, if we're adding to the anion, you're increasing the concentration of the anion, the salt, what's going to happen is, according to Le Chatelier, it's going to shift left. So it's actually going to make more acid. So the acid concentration will go up, but notice that the H3O plus stays the same. So think of it as this acid is actually staying together instead of breaking up and releasing H pluses. Same thing if you add a base, OH minus, that's going to go with the acid and neutralize. You're going to make new anion, which is going to increase the concentration of the anion, but again, the H3O plus stays the same. So that is the way the buffer works. You can add, and you're going to be adding and subtracting the acid and the conjugate, but the H3O plus stays the same, then the pH stays relatively the same. This works through the common ion effect, which is the idea that if you have an ion the same in the acid and the conjugate base, when you add either or, so if you're adding more salt, you're adding more base, you're adding more acid, it's going to shift the position of the equilibrium and therefore not add more H+. So this would cause the pH to be higher than the pH of the acidic solution, which lowers the H3O plus concentration. And the whole name of the game is keeping that H3O plus or the H plus concentration the same. So what you would look at here, the common ion effect, if you look at, this is acetic acid buffer again. Here's the acetate, acetic acid with a pH of 2.9. Here's its conjugate salt, so it's just acetate with sodium, has 8.9. But when you put them together, it's kind of like the common ions neutralize each other, so the pH kind of goes in the middle. So you notice acetic acid 2.9, sodium acetate 8.9. When you put them together, these two common anions right here, the acetate anion, kind of neutralize each other and you get a pH of 4.7. That is usually the pH of an acidic buffer. It's somewhere around, 4 to 5, somewhere in that range. So with the problems with this, the first type of problem you're going to see is just calculating the pH of just the buffer. So in this problem, you're just making the buffer. So it says, what is the pH of a buffer that is composed of 0.1 molar acetic and 0.1 molar sodium acetate? Notice again, it's acetic acid, which you're going to see a lot. So the first thing is you're going to write the equation for adding the acid to water. So that equation you have to know, HA plus water, anion A negative plus H3O plus or H plus. You're going to use a nice chart, and you're going to say, okay, I have 0.1 acid, but I also have 0.1 anion. That's kind of where this is different than the acid and water problems you were doing before. The ones you were doing before, you were doing a 0.1 here and putting 0, 0 for both products. But in this case, you not only have some acid, you also have some salt, some anion salt. So you're going to add 0.1, 0.1. Notice the water's not included because it's not really relevant here. You're going to follow your ice chart rules. You're going to use your X's because you don't know what the change is. Notice you're adding the anion because it's still a product. Those rules still apply. You're going to do your math with your X's. You're going to set it equal to Ka. So all of this is what you've been doing before. Remember, if the Ka is times 10 to the negative third or greater, which it is here, you can say the X is very small. In this case, it really helps because you can not only get rid of the bottom X, but also the top X. Remember, that only gets rid of what you're adding or multiplying by an X, not the X by itself. This one stays right here. You solve by plugging in Ka, and you're going to get 1.8 times 10 to the negative fifth H3O plus concentration. And then from there, you can use your pH equation to get a pH of 4.74. So that is the normal pH of a buffer, of a weak acidic buffer. This is another problem, same idea, but this time notice you have a pKa. So you're going to have this time it's HF, hydrofluoric acid in water. You have your beginning concentrations there. You're going to use your X's. Don't forget you're adding the anion. Set up your equations. Ka for HF is times 10 to the negative fourth, so you can say X is very small. Get rid of it. And then you'll solve. Notice, because we were given the pKa, you had to solve the Ka from there, and that's what I'm doing here. Ka equals 10 to the negative pK, so that's just another variable they may give you. Solve, and you're going to get an H3O plus concentration of 1.4 times 10 to the negative third. Use your pH to calculate of a 2.85 buffer. So again, they can be lower, a 2.85, but that is not as traditional. Usually you're going to get in the 4 range for a pH of an acidic buffer. HF just happens to be a little bit stronger acid, which is why its pH of its buffer is relatively lower. You can use the Henderson-Hasselbalch for this. So you can calculate the pH of a buffer using a Henderson-Hasselbalch equation. Remember, it's really only useful when x is very small, when it's 10 to the negative third or greater, but it's very quick. It can be something that you can do very easily, and it's the same thing that we've done before. So this is doing, where do you get the Henderson-Hasselbalch from? Where is it derived from? Not really concerned that you know where it's derived from, just that you get to this endpoint where pH equals the pKa plus the log of A negative over HA. So here you're going to calculate the pH of a buffer using Henderson-Hasselbalch instead. So you're going to calculate the pKa from the Ka given. You're going to take the pH then and plug it into Henderson-Hasselbalch, and then very easily you'll solve for the pH that way. So remember, anytime with a buffer or an acid in water, base in water, you can use Henderson-Hasselbalch as long as the Ka is times 10 to the negative third or greater. And then from here, you would solve your H3O plus concentration. If you needed it, you may not need that. So if it doesn't ask you for the H plus concentration, you don't need that. It just needs the pH. We're going to do the same thing with the other problem using Henderson-Hasselbalch. So we're just plugging it in. Notice this one actually gives you the pKa, so you don't even have to calculate it. And then you get your pH of 2.86. So which one do you use? Remember, it's when x is very small, when it doesn't really have a lot of effect when you add or subtract it. The rule that I always follow is times 10 to the negative third or greater. This means that it's not going to have that big of an effect, so therefore you can substitute the Henderson-Hasselbalch for that. So how much does the pH of a buffer change when you add an acid or base? It's going to resist changes in pH, but the pH is not going to stay the same. So again, it may change by 1/10 or so, but it's not going to be exactly the same. To calculate the new pH, what you have to figure out is how much acid, how much H plus is going to be freed and kind of added to the solution. So you're going to use stoichiometry. You're going to figure out how much the added acid adds A negative, how much it adds HA, and then finally the H3O plus. That's the key though. How much H3O plus is it adding? So what is the pH of a buffer? It has 0.1 moles of acetic and 0.1 moles of NaCH, basically sodium acetate, in 1 liter that has 0.1 mole added to it. So this time you're doing the problem you did before, and then you're adding the acid to it. So notice you have the components of the buffer first, and then the acid added to it. The base added to it second. So we set up our equation. Notice this equation, though, is acid plus base, salt. This is just the anion of the salt plus water. So when you add an acid or a base to a buffer, it's always going to be a neutralization reaction. Always, always, always. So it's important to know that neutralization reaction as well. Acid plus base yields salt plus buffer. So here you're going to do something called a Ba chart, like a lamb says Ba. The only difference between an ice chart and a Ba chart is an ice chart uses concentration in molarity. A Ba chart just deals with moles. So I'm doing 0.1 mole given for my problem. Now notice what I do with the added. Added is a change. So the 0.1 moles of NaOH added goes in my added or my change column here. Then from there, what you got to figure out is, if you're adding 0.01 moles of OH negative, you can first assume that it's all going to be neutralized, so at the end you're going to have none left. So what this is showing you here is the OH negative is completely neutralized. You add 0.01, but at the end it all goes away. Where does it go? It combines with the HA and the A negative. So what you're going to do here is you're going to take the 0.1 starting minus 0.01, and then the 0.1 plus 0.01. So this is the reactants is minus, and then the anion is plus. From here, you can plug it into the ice chart. Now in this case, you could kind of just do one, substitute in the other, but this is a two full stepper. So you're going to do your new concentrations, do it in your Ka. X is very small because it's 10 to the negative fifth. Solve for the H plus concentration, and then you're going to get your pH of 4.83. So if you recall your first pH, it's only changing by 1/10 or so. Then what you can do is solve for the pKa. This is just showing you the Henderson-Hasselbalch method. Same idea. You can choose either one. You have a lot of different paths once you figure out the H3O plus concentration. So this is just showing you in a comparison, if you did what the OH negative concentration would be, if you have 4.75 pKa for the acetic, and then you have a pH of 4.83, what it would look like on the other side. Now, a basic buffer is just what it sounds like. You're having a base now added to water, so you're going to get the conjugate acid and the OH negative, because we're talking about a base now. So you can combine a weak base with a soluble salt of the same conjugate. So in this case, you're seeing NH3, which is the weak base, and NH4Cl, ammonium chloride, which has that NH4 plus ion in it. Same idea as the acid. What is the pH of a buffer that has 0.5 molar NH3 and 0.2 molar NH4Cl? Same idea. We're using Henderson-Hasselbalch here, so make it a little quicker. So we find the pKa from the pKb. Notice if you're doing pH, you have to have the Ka for the acid. If you're doing pOH, you could use the Kb. So if you have a Ka, pH, Kb, pOH. So you're plugging in your concentrations from the problem, and you're going to get a pH of 9.65. So similarly, a pH of a basic buffer is usually in the 9-ish range, 8 to 9-ish. It can be greater or lower, but that's usually the range of that. And then just go back and do your H3O plus concentration. So a good buffer should be able to neutralize moderate amounts of acid or base. However, like we said, there is a limit. We call this limit buffering capacity. So that is the maximum amount of acid or base that can be added and still be neutralized. And the buffering range is the pH range the buffer can be effective. So obviously, if you are adding a very strong acid, it's going to have a little bit different capacity. The effectiveness of the buffer depends on the amount of acid or base and the concentration of the acid or base. So obviously, like I said, if you're adding a strong acid versus a weak acid, it's going to have an effect on the effectiveness of the buffer. So this is just comparing pHs that are relatively the same. So you have initial pH of 5, and the other buffer you're going to have pH of 4.05. And it's just showing you, what would happen if you added, in this case, you're adding a base here. And then showing you the other side. If you add the same amount of OH negative, notice the change in the buffer pH. So with the initial pH of 4.05, you get a slightly greater change by adding the same amount of NaOH as you would the buffer with a 5 starting. It's going to give you about a 1.8% change versus a 5% change. They're still effective. They're still doing the same thing. They're still doing the same job that you want. They're keeping the pH relatively the same. But obviously the buffer with an initial pH of 5 is going to have a little bit better effectiveness on that NaOH. Next thing, you're going to compare a buffer that has 0.5 moles of an acid and 0.5 moles of an acid. So this has the same starting concentrations. So you're going to add, again, some NaOH. You're going to get 5.02. Add the same amount of NaOH, you get 5.18. So in this case, what you're looking at is the percent change. It is most effective when the concentrations of acid and base are the largest. You want to have more moles of acid, more moles of base to start with. If you think about it, it's like there's more sponge, if you want to think about it when we talk about the absorbing the acid or base. So when you have the 0.5 molar acid versus the 0.05 molar, you just have more moles of acid and the conjugate available to absorb the added NaOH. But again, they're still effective. They're still doing their job. One is just slightly more effective than the other. So a buffer is most effective when the acid and base are equal amounts, and when the concentration is greater. So we talked about the buffer being most effective between 0.1 and 10. When you look at the Henderson-Hasselbalch equation and you say the lowest pH of 0.1, highest pH of 10, you see the effective buffer range is a pKa of plus or minus 1. That's where you want to have the buffering range in there. If you get anything higher, anything lower, it's going to be less effective. So in choosing an acid to make a buffer, you're actually going to choose one with the pKa closest to the pH of the buffer. That's why acetic acid is used most often, because its pKa is closest to what we want. So if we look here, which of the following acids would be the best choice to combine with sodium salt to make a buffer with a pH of 4.25? Well, what you want to look for is what has the pH closest, 4.25. So if we look here, formic acid has the closest desired pH, so it would be the most effective buffer. So this question, what ratio of sodium NaCHO2 would be required to make a buffer with a range of pH of 4.25? So we take formic acid here with a pH of 3.75, plug it into Henderson-Hasselbalch, and you see the ratio should be 3.24. So when it asks for a ratio, remember it's acid to anion. So that's actually this whole thing is the X. It's a ratio. It's something over something, division. It's a ratio of acid to buffer. So you can just solve and get the ratio number of 3.25. So to make a buffer with a pH of 4.25, you would use 3.24 times as much salt as you would acid. So buffering capacity is the amount of acid or base that can be added without destroying the effectiveness. It increases with concentration of the components. As that ratio approaches 1, the ability improves. Buffers that need to work mainly with added acid generally have a base concentration higher than the acid, and then the opposite is true when you're adding base. It's going to have an acid greater than the base. So if we look here, a concentrated buffer can neutralize more added acid or base than a dilute buffer, and the real reason is look at the amount of free anions and H pluses that are there just to kind of absorb the added acid or base. So a titration is an experiment. It's a technique where you add a substance of known concentration to a substance of unknown, and what you're looking at is usually it's with acids and bases because you're looking at the neutralization point. So an acid-base titration, which is the most common, is where you take a solution of unknown concentration, known as the titrant, added to a concentration of known, a substance of known concentration. We use a burette to do this. A burette kind of looks like an upside-down dropper, and it has a little nozzle that adds substance or stops it. The reaction is complete when you hit the end point or the equivalence point. You're going to use an indicator, which is kind of like a dye that changes color when a pH change happens in the solution, and that's how it helps determine the equivalence point. And the key to titration is the equivalence point. It's when the moles of the H plus equal the moles of the OH minus. So what can happen is, if you know, for example, there are 5 moles of OH minus in a solution, then you can add H plus until the equivalence point, and at that point you know there are 5 moles of H plus, and then you can use that to calculate what the original concentration of the acid was. So this is what the burette looks like. This is actually the picture, and this is the drawing. It's like an upside down dropper. It has a little nozzle here that you turn and it lets drops out, and you just start to add known concentration. Usually you have some kind of stir bar and that's stirring it, and then once the pH changes to a certain degree, usually it's a 7 or whatever you need the pH to be, it's actually going to change color, and that's the indicator that changed color. So that's how you know the pH has changed. You stop, you measure how much titrant you use, and that's going to how you're going to calculate the other known concentration. When you do this, a lot of times you're going to make something called a titration curve, which is a plot of pH versus amount of added titrate. What it's going to look like is an S curve. So I'm going to show you a picture in a second. And there's going to be an inflection point on the curve, which is the equivalence point. Prior to this point, the solution is in the flask is in excess, so the pH is closest to its pH. And then once the equivalence point is reached, you're going to get a huge jump in pH. If you have a neutral salt, the pH will be 7. Of an acidic salt, it'll be less than 7, obviously, and a basic salt will be greater. Beyond the equivalence point, the unknown solution is in excess, so the pH is going to go up to the opposite way. So this is what a titration curve will look like. Notice I said it looks like an S. So here is where you're adding. The pH, the buffering part of the pH is resisting. At this point right here is where you have overcome the capacity of the buffer. So you notice the pH jumps very, very quickly. That's where you kind of get the S, and then it goes into its basic range up here. So the equivalence point is the halfway between the jump. That's what I kind of call it. You're going to mark the point where it is about halfway with the jump. And what you need with the equivalence point is not only the pH at that point, but the amount, the volume of base added. So this is a real titration curve. Again, they're always going to be S-shaped. Would be adding a base into an acid. If you're adding an acid into a base, it's going to be opposite of this, but you start with a low pH, It is increasing very slowly, but it's still in that buffering range. You hit the buffering capacity, then it jumps, and then we go into the base here. So halfway, the equivalence point about here would be the equivalence point. So if you titrate 25 milliliters of 0.1 molar HCl with 0.1 molar NaOH, you're going to be able to figure out what the unknown concentration is. Now, when you do this, every single titration problem is going to be an acid plus base yield salt plus water. So you see that here. Acid plus base, salt plus water, every single time. You can calculate the initial pH because all you know at this point is the pH of the HCl, the amount of the HCl, so I get a 1. And then what you're going to do is figure out the initial moles of HCl, and that's because you're going to figure out how many moles of OH minus is that HCl absorbing. So this is all before the equivalence point is reached. You take the liters of added NaOH times the 0.1 mole of NaOH, and this gives you how many moles of NaOH added. And then what you're going to see is, did those moles of NaOH get absorbed, right? So you're going to say, okay, how much HCl do we have? 5 times 10 to the negative 4th. Then you subtract and you figure out which one's left over. You have 2 times 10 to the negative 3rd moles HCl in excess, so it's still acidic. And what's going to happen is you're going to keep adding and keep adding, and it's going to keep neutralizing, and the pH is going to stay the same. So we call this a successive titration. This is we're going to look at piece by piece by piece. Notice what you generally want to figure out is, we're at the equivalence point. How many moles of NaOH do you have? How many moles of NaOH are in excess? How many moles of HCl do you have? How many moles of NaOH are in excess? So you're going to keep doing these problems until you figure out what the pH is where it jumps. We will do these problems together. Don't panic if you're looking, but we will do these. But what you got to remember is you're always trying to figure out how much moles of HCl do I have? How much moles of OH minus do I have? So if we look at this in terms of a graph, you start out with a pH of 1. You haven't added any NaOH. Once you've added 5 milliliters, your pH is 1.18. And then it's going to slowly increase, pH of 1.37, 1.6, 1.95, and then all of a sudden it's going to jump. So after you've added 25 milliliters of NaOH, that's where you've hit your equivalence point, and then above which the pH is going to be in the base range, because every time you add more now, you're just adding more and more base, and there's no acid to be neutralized. So this is what the curve would look like. This is your equivalence point. This is where the moles of OH minus are equal to the moles of H plus. So this is just the same kind of idea. You're adding a HCHO2 to NaOH this time. You're going to have to use a ice chart here though, because HCHO2 is a weak acid. So you're going to have to kind of figure this out using an ice chart, using the changes in the ice chart. 25 milliliters again, ice chart before equivalence. How much are you adding? How much NaOH is left? How much leftover H plus do you have? So what's the pH? So every time it's like a sequential dilution, we call it a sequential titration. So you're going to have to do an ice chart over and over and over and over again and figure out what the new concentrations are. We will do this together. Don't be panicking. But in general, you're just going to calculate the concentrations at each point, calculate the pH of each point. So now we're at 25 milliliters of 0.1 molar HCl added. How much is left? How much is in excess? What is the pH at that point now that you know how much is left? And this is what the graph would look like. So we started at an initial concentration of 0.0025 and a pH of 2.37. You added 5 milliliters of NaOH. Your pH was 3.14. You did a couple of points, and you're still in the acidic range. You're still adding a little bit. It's still being buffered. One note: the pKa is equal to the pH at half the equivalence point on this graph. Then you hit your equivalence point. Your pH is 8.23. Above this, it's all going to be basic, and then here's your equivalence point right here. That's where the moles of H plus equals the moles of NaOH. Notice in this one, the equivalence point is a little bit higher than 7, and that's because you started with a weak acid. It's not going to be as neutral as it would if you're adding a strong acid and a weak base. So this is just doing the same idea, the weak acid with the strong base. The initial pH is a little bit higher, because you're gonna have a weak acid, and then remember that the equivalence point is actually going to be a little bit higher than 7 because it's going to be more on the basic side than it is on the acidic side. And then half neutralization pH at the halfway point. Remember, pH equals the pKa. When you titrate a weak acid with a strong base, remember that equivalence point is going to be a little bit higher. For example, calculating the volume of added base like 4.8, and then when you go up to the total liters, it's going to be a little bit higher, and the OH negative is going to be in excess. So at 40 milliliter sample of 0.1 molar is titrated with 0.2 molar KOH, calculate the volume at the equivalence point. So for these problems, remember, at the equivalence point, the moles of H plus are equal to the moles of OH minus. So what you essentially have to figure out is how many moles of each do you have. So if we use stoichiometry, we can figure out we have 0.02 liters of KOH, and which is 20 milliliters. And then you can figure out, again with stoich, you have 0.001 moles of KOH. We're going to use the bar chart before, after added. You're starting with 0 moles of OH minus because you're essentially adding it at the beginning. This is your change. Remember, it's all been neutralized. And then here, you're going to minus your 0.003 minus 0.001. You get your final concentrations, and then here you're going to do your normal Henderson-Hasselbalch to get the pH of 2.67. So at the halfway equivalence point, remember, is the pKa. So we're kind of doing the same thing. 40 milliliters, 0.004 moles. So at half equivalence, the moles of KOH are half the moles of HNO2. So if it starts at 0.004 moles, the added is 0.002 moles. It's all neutralized. Do your change. And then you're going to use Henderson-Hasselbalch to figure out the pH at that point is 3.15, sorry. The titration curve, remember, of a weak base with a strong acid is going to be a little bit higher. It's going to be a little bit shifted. So you're starting with a base. It's going to be a little bit higher pH. And then you're going to get a strong drop into the acidic side. For a polyproduct acid titration, you're going to have 2 jumps. So you're going to have 2 equivalence points, 2 humps, 2 S's, however you want to think about it. Because you're kind of buffering those H pluses sequentially. Remember, you have 2 Kas. The closer the Kas are to each other, the less distinguishable the equivalence points are, and you can kind of think of them the same. The general method for monitoring pH during a titration is to measure the conductivity of the solution. The endpoint is reached when the equivalence point of the titration is at the inflection point. We can also use an indicator to do this. So this is if you're going to do it with this is the conductivity measuring indicators, or when the color changes. I would say the conductivity measuring is a little bit easier in terms of you would use a computer, and that would help you really be very specific, whereas an indicator you kind of have to use your judgment and the color judgment, so it makes it a little bit more difficult. So many dyes change color depending on the pH of the solution. These dyes are weak acids, and what happens is the indicator is going to change color when the pH changes color at a certain range. So this one, phenolphthalein, is probably the most common. It's the one that's going to be a little pinky. And phenolphthalein changes pH around 8 to about 13. So it's going to be clear, clear, clear. And then as soon as you go past 7 and get into the H range, it's going to be light pink. So we use this one the most often. This is when you have a strong acid and a strong base being titrated. So that's a very, very common one. Methyl red is actually a cool one because it changes from a pink to a yellow. So it's constantly going to have a color, so it's a little bit easier to track the change. For the most titrations, the titration curve shows a very large change in pH for a small addition. An indicator can therefore be used to determine the endpoint, and it's really going to help you figure out where that is. So here's the different indicators, and you see their color changes at certain pH ranges. So like, for example, crystal violet is going to change color between 0 and 2. So if you're adding a base to anything, this is not going to help you at all because it's not even going to get into the basic range. The one we just talked about, phenolphthaleins here, about an 8 to 10, 11, something like that. Phenol red's very common. That really does the neutralization, the 7 range. You do not have to memorize these. They will kind of give you an idea, but remember, if you're picking an indicator for a titration, you want to pick where the color is going to change at the equivalence point. So if the equivalence point is going to change at a pH of 4, you want to find something that's going to change color at 4, like bromophenol blue, something like that. Solubility equilibrium is very intertwined with acid-base equilibrium. It's the whole idea that when things are in solution, you can apply the same concepts because the solutions and the solvents are going to dissolve and redissolve. You have a KSP, a solubility product constant, same as the KEQ, Ka, all those Ks that we've used. The only real difference is you're going to start off with a solid, which you're not going to include in the expression. Remember, solids and liquids aren't included. So you're really only going to include the anions and the cations. Remember to have them balanced. So if you have Na2O, there's actually 2 Nas, so you have to take that into account. So, for example, here's PbCl2. The PbCl2 is solid. It's going to dissolve into its ions. And then you're going to write the expression. Remember to have that 2 there because there is going to be 2 CO minuses when you go ahead and do that. You're going to get KSPs in, again, a chart given somewhere. So you just generally have to be able to use them for the specific solid. Molar solubility is the solubility or the amount of solute that will dissolve in a given amount of solution. The molar solubility is the number of moles that will dissolve in a liter of solution. And we've kind of done this. You're not really going to have to use an equation here. Just kind of understand in general what molar solubility is. So it says calculate the molar solubility of PbCl2 in pure water at 25 degrees. So you have dissolution equation, you have your KSP expression, you have your ice chart. Notice the only real difference is instead of X, you're supposed to use S's if it's solubility. So just a little bit different there. But the same, it's kind of the same. You take your expression, you take your S's, you solve, and you plug in to get the concentration. Same idea with this problem. You have your equation, your expression. This time it actually gives you the change, so you're actually be able to put the change in, make sure you're multiplying by the coefficient, and then you can solve, plug in, and solve for KSP in this case. So molar solubility is related to KSP, but you cannot always compare them. In order to compare, the compounds must have the same dissociation stoichiometry. This is where the common ion comes into effect. If it has a common ion, it's going to decrease the solubility of that substance. So the addition of Cl to Cl minus shifts the equilibrium to the left and makes this overall less soluble. So here we're calculating the molar solubility of CaF2 in 0.1 mole of NaF at 25 degrees. So you have your equation, you have your expression, you have your ice chart. Notice, remember you're using the S's, and you have 0.1 at equilibrium, so you're going to plug that into your chart, plug it into your expression, solve for your S, and you get the solubility of 1.4 times 10 to the negative 8. So insoluble ionic hydroxides, the higher the pH, the lower the solubility. And the lower the pH, the higher solubility. They're opposites. So if you're going to look at an equation where you're having an OH in the dissolved salt, the insoluble, remember OH negative hydroxides a lot of times are insoluble. So for insoluble ionic compounds that contain anions of weak acid, the lower pH causes them to have a higher solubility. That's kind of why, if you ever wondered, most hydroxides are insoluble, but for some reason when they're in their bases, they're very soluble, and this is kind of the idea why that happens. Precipitation, remember, occurs when the new substance that is made, the product, is not soluble in water. We can figure out whether something will be, or whether precipitation will occur by comparing the Q and the K. Remember, the Q, the reaction quotient, is just when you're dealing with initial concentrations, and the KSP is obviously the solubility at equilibrium. So when the Q equals the K, the solution is saturated, there'll be no precipitation. When Q is greater than K, there will be no precipitation. When Q is less than K, there will be no. When Q is greater than K, the salt will precipitate. Some solutions with Q greater than K will not precipitate unless disturbed. These are called supersaturated solutions. Remember, they're not really dissolved. It's just the temperature is so high that it causes them to be able to kind of suspend. And this is showing you supersaturated solutions. They're kind of cool. When you kind of put the C crystal in or you hit the side, it'll make this really cool design. A solution containing several different cations can be separated by reagents. This is where we have, they call it sequential separation, you're causing things to be precipitated out. You will not really see these, but what you can see here, you're seeing how it's going to come out of the seawater. You use the Q, the quotient, to figure out how that's going to come out. Again, these problems are not really going to be on the exam, but just in case you see them, the Q, remember, is always just the beginning concentration. So I'm just going to show you this. This is what qualitative analysis is. This is where you're going to use selective precipitation to pull out ions. It's kind of the same where if I give you a mixture of substances, you use different separation techniques. But in this case, you're going to use different additives, different chemicals to add to make things precipitate out. So you see here, you start with a solution that has a mixture of 8 compounds A, B, and C. You add the first precipitating agent, which is just something that when it combines with one of these colored dots, it's going to cause it to precipitate. In this case, you see it causes the blue to come out. You decant and filter to get that out. Then all you have left, notice, is the red and the black dots. You add another precipitating agent, causes the black to be precipitated out. You decant again, and then you just have the A in there. So you're adding something called a precipitating agent, which causes a non-soluble solution to form, and it pulls out one ion at a time. This is what it looks like in the big picture, just ways of precipitating things out. Basically, if you know your solubility rules, you can do this. Because basically, if you just add something that has a non-solubility with one of the ions, that ion will be pulled out. So this is just the general rules for this. Again, group 1 cations are Ag+, Pb, 2+, Ag2, 2+. Don't really have to memorize these if you just know your solubility rules. If you know your solubility rules, it's going to tell you what ions can be used to precipitate things out. So if you want to take a look at these groups, go ahead. But again, if you just know your solubility rules, this is really going to help you with that. Again, complex ions are not a major part of the AP exam. The complex ion is right here. So it is basically a compound that has an overall charge. We call it a complex ion. It's a very, very big ion. I guess the word tells you it's a complex ion. We call these ligands. They mostly have a ion or molecule attached, and we call that a ligand. If a ligand is added to a solution that forms a stronger bond than the current ligand, it will replace. If you just treat the complex ion like any normal ion in terms of a problem, it's going to help you. It's just going to work out. If you use a nice chart and just use a complex ion as a normal ion, it's going to go ahead and do what you want it to do. So the reaction between an ion and ligands to form a complex ion is called the complex ion formation. It has its own constant, Kf. But if you notice, it follows the same rules. You have the product ion over the reactant ions, and there's really nothing different with it. So don't get too intimidated by it. This is just giving you the Kf's of some complex ions. This would have to be given. Definitely don't have to memorize these, but really just treat them like any other ion you're used to. So if we do a problem here where you have 200 milliliters of 15 times 10 to the negative third molar CuNO32 is mixed with 250 milliliters of 0.2 molar NH3. What is a Cu2 plus at equilibrium? So you have your equation, which most likely will be given. You have your expression, which you can write. Just treat the ion as normal. Plug in the information from the problem, and you'll go ahead and get your Kf, and you'll get all your equilibrium concentrations, and that way you can just solve for the x, and you're going to get 2.7 times 10 to the negative 13th. So the solubility of an ionic compound contains a metal cation that forms a complex ion and increases in the presence of an aqueous ligand. So if we see here, we have AgCl breaking up into its components, and then we have the Ag plus going ahead and forming with ammonia to make the complex ion. So adding the NH3 increases the solubility of Ag plus in the solution with the complex ion. Remember that an amphoteric substance is anything that can be an acid or a base. Many metal hydroxides are insoluble. All become more soluble when you're added to the acidic solution. So that's how some of those hydroxides that normally wouldn't be soluble are, because you're adding them to the acid, and that's how they serve as amphoteric. They can behave as an acid or a base. This includes AlOH, Cr, OH2, ZnOH2, all those things that we're used to. Don't really have to know these details of how Al3+ does it if you just understand the generalities of the amphoteric nature.